now in, this is section 7.4, and it's called Determining Chemical Formulas. And really what we're going to look at is determining the empirical formulas of compounds. And so let's just start with the problem. So a lot of times what we'll get is we'll get percentages of an element in a compound. And this is a little bit more realistic of the type of data you might get from a chemistry lab. You could analyze a sample, find it's 92.26% by mass carbon, 7.74% mass of hydrogen. So we know it's carbon, we know it's an organic compound, and it's carbon and hydrogen, but we don't really know what it is or how it's bonded. So our first step in determining the empirical formula, and again the empirical formula, smallest whole number ratio. So let's look actually at the definition here first. So the empirical formula represents the smallest ratio of elements present in a compound. So like when we write sodium chloride is an empirical formula because really remember that ionic structure is a vast lattice. But the smallest ratio or the smallest repeating unit for what we call for an ionic compound like this would be sodium chloride. Now molecular formula is actually what is there, all the stuff that is there. And again, this is molecular because it's normally for a covalent compound. Say we had ethane, which is C2H6, and it's bonded like this. So there's two carbons bonded together, hydrogens all around. So the real molecular formula would be C2H6 because there's two carbons, 6 hydrogens. That is actually what's there. That's a molecular formula. But we could also represent it as an empirical formula, and that would be CH3. Now CH3 doesn't exist because carbon doesn't have a complete octet. There can't just be CH36, but it is the smallest ratio of this molecular formula. So going back to our problem, we have a similar example where we have some carbon, we have some hydrogen. First step is we are going to assume a sample size. Assume we have 100 grams. Why do we want to assume we have 100 grams? Well, because then we can get these percentages into mass amounts. So if I had 100 grams of carbon, or 100 grams in my sample, and it was 92.26% carbon, well then I have 92.26 grams of carbon. And if I do the same for my hydrogens, I have 7.74 grams of hydrogen. So we can change them both to a mass to begin with. And you can probably guess what we're going to do next. Well, we can't compare them based on mass, right? The percentages, we can't compare them. We can't compare them based on masses, but we can compare them based on moles. So I'm going to take the molar mass of carbon from the periodic table, 12 grams, and that's in 1 mole of carbon. And again, if you need a periodic table, you can now just pop open a periodic table, find carbon, notice it's 12.01, well, 0.11, hydrogens over here. We have the molar mass on top there. So you will want to reference a periodic table. I shouldn't say might, you will. So I'm dividing it by its molar mass. Same thing for hydrogen. I'm going to round it off to the hundredth, so it's 1.01 grams of hydrogen in every 1 mole of hydrogen. Now I divide them out, and I get the amount of moles I have. So I have 7.681 moles of carbon. Okay, really I probably should just carry it out 4 significant figures. Oh, I did. Never mind. I'm doing it right, not even knowing. And 679 moles of hydrogen. So my first step, number 1, was assume 100 grams. My second step is this, number 2, convert them both into molar amounts. Now that we have them in molar amounts, my step 3 is going to be to find a ratio. The ratio means we want a ratio between these things, so I'm going to divide by the smallest amount. The smallest amount is 7.679, so divide this by 7.679. Well, that is going to be 1. So for every 1 mole of hydrogen, there's 1 hydrogen. That makes sense. 7.679 here, and I get a value that's 1.0003 carbons per every 1 hydrogen. Well, that is pretty close to 1. So if we get a value that's 1.00003, well, we can just cut that off and assume it's 1. And we will have numbers that aren't going to come out perfectly to whole numbers, but are going to be very, very close because, again, these are laboratory measurements. And so there is some error in the testing form. So we get 1 carbon to 1 hydrogen. What that means is our empirical formula is CH. There's 1 carbon for every 1 hydrogen. Now we'd have to go through further analysis, try to figure out how it's bonded and what the molecular formula is, but this is the way we figure out the empirical formula. Okay, good? More. Okay, you can also have scenarios where they actually give you the direct masses. They say it's 13.5 grams of calcium, So they're not giving me the percentages. A lot of times they give you the percentages. If they don't, they'll give you the masses directly. And if they give you the masses directly, like this problem, well, really, it just saves you one step. It actually should be easier for you. Because if they give you the masses directly, well, then you skip to that step 2. So I don't have to convert these into mass amounts because they're already in mass amounts. So I can just start dividing by the molar masses. So I have 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. First thing, since I already have masses, is let's convert them to moles. So going back to my periodic table, calcium is 40.08 grams of calcium. Every 1 mole, if I divide that out, I get 0.33. Okay, and I just did the other ones quick, so you didn't have to wait for my slow, messy fingers here. So we have each of these values in mole amounts. So I have 0.337 moles of calcium. Now I'm going to divide by the smallest value, and the smallest value here is this 0.337 moles of calcium. So I get a ratio for calcium of, well, calcium is 1 to 1, so the smallest one is almost always going to be 1 here. Divide 0.675 by 0.337 moles of calcium, and I find for every 1 calcium, there's 2, comes out almost perfectly to 2 oxygens per 1 calcium, because I'm dividing by calcium. So it's 2 moles of oxygen to every 1 mole of calcium. Last one, again, I'm dividing by calcium, and I get 1.98 hydrogens. Well, 1.98, again, we're going to be in that scenario, well, 1.98, we're going to round that up and say, well, that's pretty close. We'll call that 2 hydrogens to every 1 calcium. So now I have my empirical formula. I have 1 calcium for every 2 oxygens to every 2 hydrogens. And so then I could write that out as my empirical formula. Calcium, 2 oxygens, and 2 hydrogens. And maybe if we look at that and I have some experience in chemistry, I can say, well, you know what that compound is? That is actually calcium hydroxide, like this. I'm going to do one more empirical formula problem. And this one's a little bit more tricky. So what we're going to be given here is we're going to be started off with percentages again. So we have 57.14% carbon. A sample is 6.16%. Let's see, hydrogen. We have 9.52%. Nitrogen. And 27.18% oxygen. So we have 4 different percentages here. Again, now, if they go back to giving you percentages, we know what to do. We assume 100 gram sample size. We start changing these into masses. Okay, so I have them written out here. The 27.18 grams, the nitrogen into grams, hydrogen into grams. Again, the same actual numerical values. We just multiplied that by 100 to get a mass in grams. Now what I'm going to do is divide each of these by their molar mass as represented on the periodic table. For carbon, it's 12.01. Hydrogen is 1.01. And I'm just going to go down and fill these out. So here we have them each divided by their molar mass. The molar mass is on the periodic table. Again, we put these into the calculator, and we're going to get some mole values. Okay, so now I divide them all, and I got moles. And one thing that people do here, sometimes they forget this last step, and they start trying to round off these values and say, well, this is about 5 to 6. That's not what we want to do. Remember, after we convert them to moles, then we have to find a ratio of how these things are bonded. So we're going to take that smallest value, this 0.68, and we're going to divide all of the values by that smallest number, so 0.68 moles of nitrogen. That means there's going to be 1 nitrogen in the compound. That's the ratio, 1 nitrogen to 1 nitrogen. Divide my oxygen by this value of nitrogen, and what I get is a value that's about 2.5. I don't really like that 2.5 oxygens. I'm going to come back to that. I'm going to divide this by 0.68. And this is, again, moles of nitrogen, so we're comparing to the ratios of nitrogen. I get 8.97. Okay, that, I think I'm pretty comfortable with calling that 9. Again, if they come really close to that value, we can round them off. We're going to have to look at that oxygen value, though, because that is not quite. And 7 moles, or 7 carbons. So we have 7 carbons to 9 hydrogens to 1 nitrogen so far. Let me clean that up a little bit. And all we have to do is 2.5 oxygens. Oof. Well, if we get a value that comes out like that to exactly like half or potentially sometimes we see a third, something coming out to like 1.33 repeating. That tells me that this is a different ratio. We don't like a 2.5. I don't want to round that up or down. So what I'm going to do is take this whole thing and say, you know what? That must actually be by 2. So I'm going to have to go back. And if I multiply that one by 2, I'm going to have to multiply all of these by 2. And so we don't have a 2-1 ratio. We have a 2 nitrogen ratio. So if I go down and multiply those through, we have 14 carbons to 18 hydrogens to 2 nitrogens and 5 oxygens. So we have to be careful, be watchful of those. If the values come out really close to a whole number, we round it off. But if it's halfway in between, then we have to probably double the values so we do get some nice whole numbers. So here are the values I have. I might spend some time trying to figure out how these things are bonded together, but this is, in essence, my empirical formula. Right now it's not in a pretty form by any means. But our next step would be to try to figure out how these things are bonded together.